Hello there, and welcome to Simple Sleepy Science. Tonight, we're exploring something you're seeing right now. Color. It's bouncing off everything around you, painting your world without you even thinking about it. But here's the thing that might surprise you. Color doesn't actually exist in the objects you're looking at. Not really. It's being created entirely inside your brain, right at this moment. Now, let's settle in and explore something that will change how you see your world. Get comfortable, because what we're about to discover is beautifully strange. If this brings you calm, if you enjoy these quiet journeys through science, please hit that like button and subscribe so you don't miss tomorrow's story. And leave a comment telling me where you're watching from and what time it is there. I love knowing you're out there, sharing this wonder with me. There's a color you see every day that shouldn't exist. It's called magenta. You know it. That pink-purple shade between red and violet. You've seen it in flowers, in sunsets, on screens, in art. It feels as real as any other color. But here's what makes magenta special. It has no wavelength. Think about that for a moment. Every other color you see exists somewhere on the spectrum of light. Red has long waves. Orange, yellow, green, blue, violet. Each one has its place, its own specific wavelength that scientists can measure. They live on a line from one end to the other. But magenta isn't on that line. It can't be. Because magenta is what happens when your brain sees red and violet at the same time. Colors from opposite ends of the spectrum, and decides to invent something completely new to make sense of it. Your brain is lying to you, but in the most beautiful way possible. When light hits your eyes, it triggers 3 types of cone cells. One responds to red wavelengths, one to green, one to blue. Every color you see is your brain interpreting the mixture of signals from these 3 types of cells. When you look at yellow, you're actually seeing red and green wavelengths together, and your brain creates the experience of yellow. That's normal. That's how color works. But magenta breaks the rules. There's no wavelength between red and violet because they're at opposite ends. There's no light that can trigger both at once in nature. So when your red and blue cones fire together without the green, your brain does something extraordinary. It fills in the gap. It creates a color that doesn't exist in the rainbow, that can't exist in pure light, that only exists as an idea inside your mind. This isn't just about magenta though. It's about everything you see. Color isn't a property of objects. A red apple isn't red. It's just absorbing every wavelength except the ones we call red, and those bounce into your eyes. The apple itself is colorless. It's just matter reflecting light. Your brain is the painter, taking those wavelengths and turning them into the experience of redness. You're not seeing the world as it is. You're seeing your brain's interpretation, its creative translation of electromagnetic waves into conscious experience. Every color is invented. Every shade is constructed. You're living inside a reality your mind is building from scratch, moment by moment. And if your brain can invent magenta, a color with no basis in the physical spectrum, what else might it be creating? What other aspects of your reality might be beautiful constructions rather than objective truths? This is where science becomes philosophy, where the question of what we see becomes the question of what is real. Tonight, as you explore the science of color with me, you're going to discover that seeing isn't believing, it's creating. And you've been an artist all along, painting your world without even knowing it. Let's keep going deeper into this rabbit hole, because magenta is just the beginning of how strange color really is. Now, let's look up at the sky, that endless blue stretching above you. Except, it's not blue, not really. In fact, it's not any color at all. The air you're breathing right now, the atmosphere wrapped around our planet, is completely colorless, transparent. If you could hold a jar of pure air and look at it, you'd see nothing, just clear space. So why does the sky look blue? It's another trick, another beautiful lie your eyes and brain are telling you together. Here's what's actually happening. Sunlight looks white to us, but it's really a mixture of all colors traveling in waves. When those waves hit Earth's atmosphere, they slam into tiny molecules of nitrogen and oxygen. These molecules are incredibly small, smaller than the wavelengths of light itself. And when light hits something that small, something interesting happens. It scatters, but not all colors scatter the same way. This is the key. Blue light has short, choppy waves. Red light has long, smooth waves. When blue light hits those tiny air molecules, it bounces around like a pinball, careening off in every direction. Red and yellow light, they mostly just slide past, barely disturbed, continuing straight down to the ground. So, blue light is bouncing around up there, scattered across the whole sky. No matter where you look, blue light is ricocheting into your eyes from every angle. The sky appears blue because blue is what's being scattered most. The air itself hasn't changed color. It's still colorless. But the light passing through it has been sorted, filtered, scattered into this dome of blue above you. Now, here's where it gets even better. Think about sunsets. Why does the same sky that's blue during the day turn orange and red and pink at dusk? Distance. When the sun is directly overhead at noon, its light travels straight down through the atmosphere. Short trip. But when the sun is near the horizon at sunset, its light has to travel sideways through much more atmosphere to reach you. Miles and miles of air molecules. All that extra distance means even more scattering. The blue light gets scattered so much, bounced around so many times, that it scatters away completely before reaching your eyes. It's gone, lost in the atmosphere. But red and orange light, with their longer wavelengths, can push through. They're strong enough to make the journey. So, at sunset, you see the colors that survived, the warm colors that couldn't be scattered away. The same scattering that makes the sky blue during the day makes it red at sunset. Two completely different colors from the same process, just at different distances. Here's the proof that the sky's color is an illusion. Astronauts in space, above the atmosphere, see a black sky even in daylight. There's no air up there to scatter the light. The sun is blazing, stars are visible, but the sky itself is pure darkness. The blue you see every day only exists because you're at the bottom of an ocean of air, looking up through layers of scattering molecules. Stand on the moon and look up. You'd see blackness. Stand on Mars with its thin atmosphere, and look up, you'd see a butterscotch sky. The color of the sky isn't a property of the sky. It's a property of what the sky is made of and how light moves through it. Everything you see is a negotiation between light and matter, filtered through your eyes, interpreted by your brain. The blue sky is beautiful, but it's not really there. It's another painting your mind is creating from the raw data of scattered photons. You're seeing something that only exists because you're here to see it. But there's something stranger about blue, something that reaches back thousands of years into human history and raises a question that still puzzles scientists today. Ancient people didn't have a word for blue. Not the Greeks, not the Chinese, not the Japanese, the Hebrews, or ancient Hindu cultures. They described the sky as bronze, as iron, as the color of darkness. Homer called the sea wine dark in the Odyssey. Wine dark, not blue. And he wasn't alone. Ancient texts from around the world describe the ocean, describe the heavens, but never once use a word that means blue. The ancient Egyptians were the first culture to create a word for blue, and only after they invented a blue dye. They had to make the color before they could name it. Before that, blue simply didn't exist in their language. Think about what that means. Here's the pattern scientists discovered when they studied languages across the world, from isolated tribes to ancient civilizations. They found that color words appear in almost the exact same order. Every language starts with words for light and dark, then red, then yellow and green. Blue comes last, always. In nearly every human culture that's ever existed, blue is the final color to get its own word. Why? Why would humans everywhere struggle to name blue when it's the color of the sky above them every single day? Some researchers believe ancient people genuinely saw the world differently. Not that their eyes were different, but that their brains processed color differently because they didn't have categories for it. Language shapes perception. If you don't have a word for something, your brain might group it with other things instead of seeing it as separate and unique. The Himba tribe in Namibia has no word for blue. When researchers showed them cards with 11 green squares and 1 blue square, they struggled to find the different one. To them, it looked like 12 similar green shades. But the Himba language has many words for different types of green that English speakers see as identical. Show them cards with subtle green variations we can't distinguish, and they spot the different one instantly. We see what we have words for. We distinguish what our language tells us is worth distinguishing. So, did ancient Greeks look up at the sky and see something other than blue? Did they experience it as a shade of darkness or a metallic bronze glow? We'll never know. We can't step into their perception. But the linguistic evidence suggests their experience of the sky was genuinely different from yours. Not because their eyes were different, but because their minds categorized it differently. Color isn't just in the wavelengths or in your brain's processing. It's also in the language and culture that taught you what to look for, what to separate, what to name. A child learning English learns to split the spectrum into red, orange, yellow, green, blue, purple. A child learning Russian learns 2 different words for light blue and dark blue, treating them as completely separate colors, the way English treats red and pink. And that child will see those blues as more different than an English speaker does, purely because of language. you're not just seeing color, you're seeing the colors your culture taught you to see, the categories your language built in your mind. Ancient people weren't blind to blue, they just hadn't learned to pull it out from the darkness, to give it its own identity, separate from the void. And without that category, their experience of the sky was something we can barely imagine now, something lost to time, like a color we'll never see again. And speaking of blue, here's why it was so hard for ancient people to find it. Blue is the rarest color in nature, not just uncommon, genuinely rare. Look around the natural world and you'll find red flowers, yellow birds, green leaves everywhere. But true blue? It barely exists. There are almost no blue animals, no blue flowers made with blue pigment. And the few blues you do see, like a blue jay's feathers or a morpho butterfly's wings, aren't actually blue at all. They're playing the same trick as the sky. They're using structure instead of color. Here's the difference. Most colors in nature come from pigments. A red rose has molecules in its petals that absorb every color except red. Red bounces off, and you see a red flower. Simple chemistry. But blue pigment is incredibly difficult for living things to make. The molecular structure required is complex, unstable, rare. Nature struggled for millions of years to create blue the normal way. So, instead, nature got clever. It built structures. A blue butterfly wing under a microscope looks like a tiny city of ridges and layers. These microscopic structures are arranged at exactly the right spacing to scatter blue wavelengths while cancelling out other colors. The wing itself has no blue pigment. It's actually brown. But the structure on its surface bends light, filters it, bounces it around until only blue escapes to your eyes. It's architectural color, engineered blue. Blue jays work the same way. Their feathers have no blue pigment inside them. The feather cells are filled with tiny air pockets arranged in a specific pattern. Light hits these pockets, scatters, and blue wavelengths reinforce each other while other colors cancel out. Crush a blue jay feather and it turns brown instantly because you've destroyed the structure that was creating the illusion of blue. Even blue eyes work this way. There's no blue pigment in blue eyes. The iris has a cloudy layer that scatters light, and like the sky, the blue wavelengths scatter most. Behind that layer is brown pigment. Every blue eye is actually a brown eye, wearing a structural mask that scatters blue light. It's the sky effect happening in your iris. This is called structural color, and it's how nature solved the blue problem. Can't make blue pigment easily? Build blue instead. Construct it from transparent materials arranged just right. It's more difficult, more precise, but it works. And it's absolutely beautiful. Only a handful of living things ever figured out how to make true blue pigment. Some plants managed it after millions of years of evolution. A few butterflies in South America finally cracked the chemical code. But it's so rare that when geneticists successfully put blue pigment genes into roses in 2004, it made international news. We'd never seen a truly blue rose before. They don't exist in nature because roses never evolved the ability to make that pigment. This is why blue dyes were so valuable throughout history. Blue pigment was nearly impossible to find. Ancient Egyptians had to crush lapis lazuli stones, imported from Afghanistan to get blue paint. Medieval artists paid more for ultramarine blue than for gold. It was the most expensive color in the world because nature had hidden it so well, made it so difficult to extract and create. Blue is precious because blue is hard. It requires either complex chemistry or precise engineering. Nature had to work harder for blue than for any other color, and that makes every blue you see, whether in a butterfly's wing or the evening sky, a small miracle of physics and light. Let's talk about pink for a moment, because pink has a secret that shows just how arbitrary our relationship with color really is. 100 years ago, pink was for boys. Blue was for girls. That's not a joke. That was the actual standard in Western culture. Baby boys wore pink because it was seen as a stronger, more passionate color, a watered-down version of powerful red. Blue was delicate, dainty, soft, perfect for little girls. Then everything flipped. By the 1950s, pink had become the ultimate feminine color, and blue was for boys. What happened? Marketing, fashion trends, cultural shifts that had nothing to do with the colors themselves, and everything to do with how society decided to use them. The colors didn't change. We changed what they meant. This matters because it reveals something important. The emotions you feel when you see pink or blue aren't coming from the wavelengths. They're coming from years of cultural conditioning, from stories you've been told about what these colors represent. Pink doesn't make you think of femininity because of anything inherent to pink. It makes you think that because you grew up in a culture that spent decades building that association. Go to other cultures and the meanings flip again. In China, red is luck and celebration. In South Africa, it's mourning. White is purity in Western weddings and death in Eastern funerals. Yellow is courage in Japan, cowardice in America. Same wavelengths, completely different emotional responses, built entirely from cultural context. Your feelings about color are learned, taught, constructed from thousands of small moments where you absorbed what colors were supposed to mean. And once those associations formed, they feel natural, instinctive, true. But they're not. They're cultural software running in your brain. Even the idea that certain colors go together is arbitrary. You might think orange and purple clash, but that's just because you've internalized certain aesthetic rules from your culture. Show those colors to someone from a different tradition, and they might find them perfectly harmonious. Color theory is real in the sense that some combinations create certain effects, but which effects are considered beautiful or ugly is learned. This opens up something profound. If your emotional responses to color are culturally constructed, then seeing a sunset doesn't have to make you feel a certain way. The warmth you feel isn't mandatory. It's optional. An invitation, not a command. You can experience color differently if you choose to notice the arbitrary nature of your responses. Think about your favorite color. Why is it your favorite? Probably because of memories attached to it. A childhood blanket, a parent's eyes, a special place. The color itself is just wavelengths, but you've wrapped meaning around it through experience. It's yours in a way that's completely personal and completely constructed. And if meanings can be built, they can be rebuilt. You're not stuck with the color associations you inherited. You can notice them, question them, maybe even change them. Pink doesn't have to mean anything specific. Blue doesn't have to make you feel calm. Those are suggestions, not laws. Colors are neutral until we decide what they mean. And we've been deciding for thousands of years, building layer after layer of meaning that feels ancient and true, but is really just recent and agreed upon. The wavelengths hitting your eyes are physics. What you feel about them is poetry, and you're the poet, whether you realize it or not. Now, let's zoom out, because everything we've talked about so far, every color you've ever seen, is just a tiny sliver of what's actually out there. The visible spectrum, all the colors from red to violet, makes up less than 1% of the electromagnetic spectrum. Less than 1%. The rest is invisible to you. It's there, all around you right now, but your eyes simply can't detect it. Just beyond red is infrared. Heat radiation. It's pouring off your body right now, radiating from your skin, but you can't see it. Rattlesnakes can. They have special pit organs that detect infrared, letting them see the heat signature of warm-blooded prey in complete darkness. To a snake, you're glowing, radiating color you can't perceive. Just beyond violet is ultraviolet. It's in sunlight, bouncing off flowers, but invisible to you. Bees see it perfectly. To a bee, flowers look completely different than they do to you. Many flowers have ultraviolet patterns, like landing strips guiding bees to nectar. You see a plain yellow flower. A bee sees a yellow flower with purple bullseye in the center. Same flower. Two completely different visual experiences. This means the world you see is just one version. One narrow channel of reality. Bees live in a different visual universe while walking through the same garden. Snakes see a different world at night. Even birds see more colors than you do. Most birds have 4 types of color receptors instead of your 3. They see combinations and distinctions you literally cannot imagine. Think about what you're missing. X-rays are passing through you. Radio waves are carrying signals through your body. Gamma rays from distant stars are hitting Earth. Microwaves, radar, cosmic background radiation. It's all electromagnetic energy, all technically light. Just at wavelengths your eyes weren't built to catch. Your eye evolved to see a specific range because that range was useful for survival. It's the range where the sun puts out most of its energy. It's the range that penetrates Earth's atmosphere well. It's the range where water is transparent, so you can see underwater. Your visible spectrum isn't the right range. It's just the practical range for a primate living on Earth's surface. If you'd evolved on a different planet, orbiting a different star, your visible spectrum might be completely different. You might see an infrared naturally, or ultraviolet, or some other range we can't even imagine. The colors you think of as color are just what happened to be useful for your ancestors. And here's the humbling part. You're essentially colorblind to most of reality. Not in the sense of mixing up red and green, but in the sense of missing entire categories of light that exist all around you. You're walking through a rainbow you can't see, made of wavelengths that are just as real as the ones you can detect. This should make you wonder, what else might you be missing? Not just in light, but in sound, in touch, in every sense. You're experiencing a filtered version of reality. custom-built for human survival, not for complete truth. Every creature on Earth lives in its own sensory bubble, its own private slice of what's actually out there. The colors you see aren't the only colors. They're just your colors. And that's okay. It's beautiful, even. But it's worth remembering that your experience, no matter how vivid and complete it feels, is a fraction of what's possible. But within the range you can see, colors do something interesting to your body. They change you, not just emotionally, but physically. Red raises your heart rate. Studies have measured this. Put someone in a red room and their pulse quickens. Their blood pressure goes up slightly. Red is stimulating. It makes you feel warmer even when the temperature hasn't changed. Restaurants use red in their branding because it increases appetite. Fast food chains paint their walls red because it makes you eat faster and leave sooner, cycling through more customers. Blue does the opposite. It lowers blood pressure, slows breathing, creates calm. Streetlights in some Japanese cities were changed to blue and crime rates dropped. Not because criminals suddenly became law-abiding, but because blue light reduces aggression. It takes the edge off anger before it becomes action. Pink is even stranger. There's a specific shade called Baker-Miller pink, named after the researchers who discovered its effect. Prisons painted holding cells this color and found that violent inmates calmed down within minutes. The color physically reduces muscle strength temporarily, makes aggression harder to sustain. Some prisons still use it, painting cells bright pink to manage dangerous inmates without force. These aren't just psychological tricks. They're measurable biological responses. Color affects your nervous system, your hormones, your body's basic functioning. But here's where it gets complicated. Nobody knows exactly why. Some of it is evolutionary. Red might trigger alertness because it's the color of blood, of danger, of fire. Blue might calm us because it's the color of clear skies and clean water, signs of safety in our ancestral environment. These responses could be hardwired, built into us over millions of years. But some of it is definitely learned. In Western hospitals, blue hospital gowns and green surgical scrubs were chosen because they're opposite red on the color wheel. After staring at red blood during surgery, doctors would see green after images. So, hospitals used green walls and clothing to make those after images less distracting. The calming association with medical blue and green came later, after generations of people associated those colors with healing spaces. Yellow increases anxiety in some studies, but it also improves mood in others. It depends on the shade, the context, the person's history with yellow. Some reactions are universal, some are deeply personal. And here's the real question. If you know that red is making your heart beat faster, does it still work? If you're aware that blue is calming you, does the effect disappear? Or does your body respond regardless of what your conscious mind knows? The answer seems to be both. Awareness changes the effect, but doesn't eliminate it. You can notice that red is stimulating you and still feel stimulated. You can know that pink reduces aggression and still feel calmer. The biological response happens partly below conscious control, in ancient parts of your brain that don't care what you know. But awareness gives you options. You can use color deliberately. Wear blue before a stressful meeting. Paint your bedroom walls in calming tones. Avoid red when you need to think clearly, or do the opposite. Use red when you need energy, yellow when you need creativity, green when you need balance. Color is a tool, and now that you know how it works, you can choose how to let it affect you. But there are colors your brain refuses to show you. Colors that exist in theory, but can't exist in your perception. They're called impossible colors, and they break your visual system. Your eyes work on opponent processes. Red versus green, blue versus yellow. When you see red, your red-green neurons fire toward red. When you see green, those same neurons fire toward green. But they can't fire both directions at once. It's either red or green, never both simultaneously. Same with blue and yellow. Your blue-yellow neurons point one way or the other. Blue or yellow? Pick one. Your visual system is built on this either-or architecture. It has to be. You need contrast to see anything at all. So, what happens if you try to see reddish-green? Not brown, which is red and green mixed together, creating a separate color, but genuinely red and green at the same time, in the same spot, not mixing. Your brain simply won't do it. Can't do it. The wiring doesn't allow it. Same with yellowish-blue, not green, which sits between yellow and blue on the spectrum, but yellow and blue occupying the same space simultaneously, each color remaining distinct yet together. Impossible. Except scientists found a way to trick it. In experiments, researchers had people stare at red and green images in a specific way, using mirrors and precise alignment so that each eye saw a different color in the same location. The brain received conflicting signals. Left eye said red, right eye said green. And something strange happened. Some people reported seeing a color they'd never seen before, a color they couldn't describe. Not brown, not a mixture, but something genuinely new. Reddish-green as a distinct experience, not as a compromise. For a few seconds, their brains bypassed the opponent process system and showed them the forbidden color. Others saw yellowish-blue the same way, a color that shouldn't exist but briefly did, living in that gap between what's possible and what isn't. The descriptions are always vague because language doesn't have words for these colors. How do you describe something nobody else has seen? Something that violates the rules of perception? The people who saw impossible colors struggled to explain them. They just knew they were different. New, wrong, but real. This raises questions that don't have answers. Are impossible colors actually new colors? Or are they just visual glitches? Is your brain creating something genuine, or just confused by conflicting signals? And if these colors exist even briefly in someone's perception, are they as real as normal colors? Remember, normal colors are already invented by your brain. Magenta doesn't exist in wavelengths, but feels completely real. So, maybe impossible colors are just another level of invention. Your brain stretching beyond its normal limits, showing you what happens when the rules bend. You'll probably never see an impossible color. The experiments are difficult to set up, and even when they work, the effect lasts seconds. But knowing they exist changes something. It means the colors you see every day aren't the only possible colors. There are experiences of color hiding in the gaps, in the spaces between categories, waiting for the right conditions to emerge. Your perception has boundaries, but boundaries can be pushed. And somewhere beyond what you think is possible, there are colors waiting that have no names, no place in the spectrum, no reason to exist, except that they do for brief moments in the strange space where your brain meets light. Let's come back to something simpler, something you see every day without thinking about it. Traffic lights. Red means stop. Green means go. Yellow means caution. But why those specific colors? Physics chose red. Red light has the longest wavelength in the visible spectrum. Those long waves travel farther through air than shorter wavelengths. They push through fog, rain, dust, pollution. On a misty morning when you can barely see the road ahead, red light reaches your eyes when other colors would scatter and fade. Railroads figured this out first in the 1800s. They needed signals that workers could see from long distances, in any weather. Red worked best. So, red became the universal color for stop, for danger, for attention needed immediately. When cars came along, they borrowed the railroad system. Red was already understood, already trusted. Green got chosen for go because it's on the opposite end of the visible spectrum from red. Maximum contrast. No confusion possible. Even people with red-green colorblindness can usually distinguish traffic lights because the lights are positioned consistently. Top is always red. Bottom is always green. Position backs up color. Yellow landed in the middle as a warning because it sits between red and green, both in spectrum and in meaning. Not quite danger, not quite safe. Caution, prepare, pay attention. It made logical sense. But this system isn't universal. In Japan, the green light is actually blue, not because the physics is different, but because the Japanese word for green and blue was historically the same word. When traffic lights arrived, they called it blue, even though it's technically green. The language shaped the name, even though the color stayed the same. And in some cultures, red doesn't mean danger at all. In China, red is lucky. Celebratory. Brides wear red. Money comes in red envelopes. But even in China, traffic lights use red for stop because the system is global now. Function overrides cultural meaning when safety is involved. Here's what's interesting. Your reaction to a red light is both biological and learned. Biologically, red does grab attention faster than other colors. It's high contrast, high energy. Your eyes notice it quickly. But the meaning of stop is purely learned. A child who's never seen a traffic light doesn't know red means danger. They have to be taught. The color provides the visibility. Culture provides the meaning. This happens everywhere. Warning signs are yellow and black because that combination appears frequently in nature as a danger signal. Wasps, bees, poison dart frogs. Animals evolved bright yellow with black patterns to say, "Leave me alone," and our brains evolved to notice and remember that pattern. So we use it on construction signs, on hazard warnings, on caution tape. We're leveraging millions of years of evolutionary learning. But the specific meanings we attach are arbitrary within that framework. Red could have meant go if we decided that early on. Yellow could have been stop. The physics of visibility would stay the same, but the cultural agreement would be different. Every color-coded system you interact with is a combination of physics and agreement. The physics determines what works practically. The agreement determines what it means. And once enough people agree, it becomes real. Not naturally real, but functionally real. As real as anything else we've collectively decided matters. Stoplights are simple, but they show how color becomes communication, how wavelengths become language, how physics becomes culture, becomes daily life, so seamlessly you never notice the layers. Some colors have died. They existed once, were seen by human eyes, worn by emperors, and painted by masters. Now they're gone, lost to time, to chemistry, to ethics. Colors you'll never see again. Tyrian purple was the most expensive color in ancient history. To make 1 gram of dye, you needed 12,000 crushed sea snails. Shellfish called murex, harvested from Mediterranean coasts, each one containing just a drop of the chemical that would turn fabric deep purple. The color of royalty, the color of Roman emperors. It was literally illegal for common people to wear it. The dye works were factories of death, mountains of broken shells. The smell was unbearable, like rotting fish concentrated into a toxic fog. Workers would spend their lives crushing snails to extract tiny amounts of purple. And the color was worth it. Richer than any plant dye. More permanent. A purple that wouldn't fade with washing or sunlight. Then the recipe was lost. When the Roman Empire fell, the knowledge of how to make Tyrian purple disappeared with it. For over 1,000 years, nobody knew how to recreate it. The specific species of snail, the exact process, gone. And with it, that precise shade of purple vanished from human experience. We have approximations now, modern recreations, but the exact color that emperors wore is extinct. Mummy brown was exactly what it sounds like. Ground up. Egyptian mummies mixed with oil to create paint. Artists used it for centuries, from the 1500s through the early 1900s. It gave paintings a warm, rich brown tone. Translucent. Perfect for shadows and flesh tones. And it came from grinding human remains into pigment. Some artists didn't even know what they were using. The name Mummy Brown sounded exotic, historical. They assumed it was just a name. When Edward Burne-Jones, a famous pre-Raphaelite painter, discovered his Mummy Brown actually contained mummies, he was horrified. He buried his tube of paint in his garden with a funeral ceremony. No more painting with the dead. The practice stopped. Mummies became protected. Museums preserved them instead of selling them to paint makers. And Mummy Brown disappeared. The exact color, made from that specific combination of ancient resins and human tissue, is gone. You can't buy it, can't make it legally. It exists only in old paintings, slowly fading as centuries pass. Lead white killed artists for generations. It was the brightest, most opaque white pigment available, perfect for highlights, essential for skin tones in portraits. And it was pure poison, lead carbonate. Artists would lick their brushes to keep them pointed, ingesting lead with every painting session. They'd breathe lead dust while grinding pigments, slow poisoning that caused madness, organ failure, death. We stopped using it once we understood. Modern white paints use titanium dioxide or zinc oxide. Safer, almost as bright, but not quite the same. Lead white had a warmth, a glow that modern substitutes can't fully match. It's banned now, illegal to manufacture or sell in most countries. The paintings that used it still contain it, slowly degrading. But new art can't use that white anymore. These lost colors matter because they show that color has history. Some colors require sacrifice. Some require death. Some require ethics we no longer accept. And when we choose to stop using them, those specific experiences of color end. The wavelengths might remain possible, but the actual pigments, the real substances that created those exact shades, are extinct like species we've hunted into nothing. But not all color comes from pigments and dyes. Some colors appear purely from light, doing what light does naturally. Like rainbows. Perfect, temporary, impossible to touch. A rainbow happens when sunlight hits water droplets in the air. Each droplet acts like a tiny prism. Light enters the droplet, slows down, bends. Different wavelengths bend at different angles because they travel at slightly different speeds through water. Red bends least. Violet bends most. The light bounces off the back of the droplet, splits into its component colors, and exits as a spectrum. This is why rainbows are always the same order. Red on top, violet on bottom, orange and yellow and green and blue arranged between them. It's not random, it's geometry. The physics of refraction puts each color in its specific place, every single time. You can't have a rainbow with violet on top. The math doesn't allow it. And here's something beautiful. You never see the same rainbow as the person standing next to you. Not exactly. The rainbow you see is made of light from specific droplets at a specific angle from your eyes. Move 3 feet to the left, and you're seeing light from different droplets. The rainbow shifts with you. Everyone creates their own personal rainbow from their unique position. You're not looking at one rainbow that exists in space. You're looking at a pattern of light that only exists because you're standing exactly where you are. This is why you can never reach a rainbow. Walk toward it, and it walks away. The geometry that creates the rainbow always puts it at the same angle from your eyes, about 42 degrees from the antisolar point, the spot directly opposite the sun. That angle moves with you. The rainbow stays forever distant, forever unreachable, because it's not a thing. It's a relationship between you and light and water. You can see rainbows in sprinklers, in waterfalls, anywhere water droplets catch sunlight at the right angle. Same physics, same order of colors. Some people see double rainbows, where light bounces twice inside the droplets before exiting, creating a fainter second arc with the colors reversed. Rare, but real. Ancient people saw rainbows and thought they were solid things. Bridges to the heavens, promises from gods. They didn't know about refraction and wavelengths. They just saw beauty appearing from nothing, arcing across the sky, and they made it sacred, made it meaningful. Now you know it's water and light and angle. Does that make it less beautiful? Some people think science strips away the magic. But look at what's actually happening. Millions of water droplets, each one splitting light into its components at precisely the right angle, all of them coordinating without communication to paint a perfect spectrum across the sky. And that spectrum exists only for you, from your exact location, unrepeatable and personal. That's not less magical. That's more. Because the magic is real. It's not a god painting the sky. It's light being light, following rules that have been true since the universe began, creating beauty as a side effect of physics. And you get to stand there and watch it happen. You get to see the universe doing math in color, solving equations across the sky, and calling the answer a rainbow. The ancients were right to find it sacred. They just didn't know how deep the sacredness went, how precise, how elegant, how utterly temporary and utterly reliable at the same time. Some colors make their own light. They don't need the sun or a lamp. They glow from within, creating color out of chemical energy, out of stored light, out of biology itself. Fireflies do this. Their abdomens light up yellow-green through a chemical reaction called bioluminescence. Inside their cells, a molecule called luciferin combines with oxygen and an enzyme called luciferase. The reaction releases energy as light instead of heat. Cold light, efficient light. A firefly can turn nearly 100% of the chemical energy into visible glow. Compare that to an incandescent bulb that wastes 90% of its energy as heat. Deep-sea creatures use the same chemistry. Anglerfish with glowing lures, jellyfish pulsing blue, entire ecosystems in the ocean depths, where sunlight never reaches, all lit by living things making their own colors. Some use bioluminescence to hunt, some to hide, some to communicate in patterns we're only beginning to understand. Then there's phosphorescence. This is different. Things that glow in the dark, after being exposed to light, aren't making their own energy. They're borrowing it, storing it, releasing it slowly. Glow-in-the-dark stars on bedroom ceilings work this way. The material absorbs light energy when the room is bright. That energy excites electrons to higher energy levels. Then, in darkness, those electrons gradually fall back down, releasing the stored energy as a soft green glow. It fades over time because they're running out of borrowed light. They need to be recharged by exposure to brightness. Some minerals do this naturally. Fluorite glows after being in sunlight. Some diamonds glow blue in darkness after bright light exposure. The color depends on the specific impurities in the crystal structure. Tiny defects that trap and release light in particular wavelengths. What makes these glowing colors interesting is that they reveal energy itself becoming visible. You're watching chemistry happen, watching electrons move between states, watching stored energy transform into photons. The glow is evidence of invisible processes made manifest. And it's ancient. Bioluminescence evolved independently in dozens of different species. Bacteria, fungi, insects, fish, squid. Life kept discovering the same solution to the same problem. How to make light without heat. How to be visible in darkness without burning energy inefficiently. Humans tried to copy it for centuries. We made phosphorescent paints from minerals. We extracted luciferin from fireflies to study it. We wanted to control that cold light, that efficient glow. Now we can synthesize it. Glow sticks use chemiluminescence, the chemical cousin of bioluminescence. Break the inner tube and two chemicals mix, creating light through reaction. It glows for hours, then dies when the chemicals are used up. But we still haven't matched the elegance of a firefly. Our chemical lights are one-time use. Wasteful. A firefly can produce light on and off for its entire life, powered by the food it eats, controlled precisely, used for communication in patterns of flashing that attract mates and warn competitors. Color from chemistry, light from life. These glowing colors remind us that energy and matter and light are all connected. That the photons hitting your eyes might come from the sun, or from a burning filament, or from a chemical reaction happening inside a living cell. The source changes, but the result is the same. Wavelengths, colors, light making its way to you through the darkness, painting the world into existence. Now, let's talk about the colors that might not be colors at all. Black and white. Are they colors? Scientists say no, artists say yes, and both are right, depending on how you're thinking about color. Scientifically, black is the absence of light. When no photons reach your eyes, you see black. It's nothing, a void. The default state when there's no electromagnetic radiation in the visible spectrum. Black isn't a wavelength. It's what happens when wavelengths are missing. White is the opposite extreme. It's all wavelengths combined. When red, orange, yellow, green, blue, and violet hit your eyes simultaneously in equal amounts, your brain interprets that flood of information as white. White is everything. Black is nothing. Neither one is a specific wavelength like blue or red. So, by the physics definition, they're not colors. They're the bookends, the boundaries of color. But stand in front of a painting and that logic falls apart. Black paint is a color. White paint is a color. Artists mix them, use them, treat them as essential parts of the palette. You can't paint without white, can't create shadows without black. They function as colors, even if the physics says otherwise. This paradox exists because color means two different things. In physics, color is about wavelengths of light. In art and perception, color is about experience. The experience of seeing black paint is just as valid as the experience of seeing blue paint. The fact that one is absorbing all wavelengths and the other is reflecting specific ones doesn't change how real they feel to your eyes. Here's where it gets interesting. Pure black doesn't exist. Nothing absorbs one. 100% of light. The blackest things you can see, like charcoal or black velvet, still reflect some photons. They're just reflecting so few that your brain rounds it down to black. Same with white. Nothing reflects perfectly. White paint is just reflecting most wavelengths most of the time. And in darkness, everything is black. Not because objects change, but because there's no light to reflect. Your blue shirt and your black shoes look identical in a dark room. The color is gone because color requires light. Remove light and color disappears, leaving only darkness. This makes you realize something. Color isn't in objects. We've said this before, but it bears repeating. The shirt isn't blue. The shirt is a collection of molecules that reflect certain wavelengths when light hits them. In darkness, those same molecules exist unchanged, but the blueness is gone. The color exists in the interaction, in the meeting of light and matter and eye and brain. Black and white are the extreme states of that interaction. All light or no light. Everything or nothing. They define the range within which all other colors exist. Some cultures don't separate black and white from colors. Some languages group them differently. To them, black and white are obviously colors, because why wouldn't they be? You can point to them, name them, use them. The scientific distinction doesn't matter to daily experience. So are they colors? Yes and no. Both and neither. It depends on whether you're asking about physics or perception, about wavelengths or experience. The question itself reveals how complicated color really is, how it exists in multiple domains at once, physical and psychological, objective and subjective, neither one complete without the other. Fire has color, and that color tells you exactly what's burning and how hot it is. Every flame is a chemical signature written in light. A candle flame burns yellow and orange because you're watching carbon particles glow. When wax vaporizes and burns, it breaks apart into carbon atoms. Those atoms heat up to around 1000 degrees Celsius and start radiating light. Hot carbon glows orange-yellow. That's the color of the carbon itself, heated to the point where it becomes visible. It's the same reason metal glows red when it's hot. Heat makes matter emit light, and the color depends on temperature. But blue flames are different. Natural gas burns blue because the combustion is more complete. There's enough oxygen for the fuel to burn fully, without creating those glowing carbon particles. Blue flame is hotter, around 1400 degrees Celsius. The color comes from excited molecules of carbon monoxide and other gases releasing energy as they form and break apart. It's molecular light, not glowing particles. Hotter equals bluer, cooler equals redder. This rule is universal. The coolest stars in the universe are red. Medium stars like our sun are yellow. The hottest stars burn blue-white. Same physics. Temperature determines the wavelength of light that matter emits. Objects get red hot, then orange hot, then white hot, then blue hot as temperature climbs. Now add chemistry. Different elements burn in different colors regardless of temperature. Copper turns flames green. Sprinkle copper powder into a fire and you'll see bright green flames dance through the yellow. Sodium burns orange-yellow, which is why streetlights that use sodium vapor glow that specific amber color. Potassium burns violet. Strontium burns red. Barium burns green. This happens because each element has a unique electron structure. When you heat atoms, their electrons jump to higher energy levels. When those electrons fall back down, they release energy as light. The specific wavelengths they release depend on the gaps between energy levels. And those gaps are different for every element. Copper's electrons can only release green photons, Sodiums can only release yellow-orange. The color is as specific as a fingerprint. Fireworks use this. Every color in a fireworks display comes from metal salts burning at high temperature. Want red? Add strontium. Want blue? Add copper. Want white? Add magnesium or aluminum. The explosions aren't just beautiful, they're chemistry on display. Each burst of color is billions of atoms releasing photons at specific wavelengths, coordinated by the rules of quantum mechanics into colors your eyes can catch. Scientists use this to study stars. Stars are too far away to visit, but their light reaches us. By splitting starlight into its spectrum and looking at which colors are present, astronomers can tell what elements the star contains. Dark lines in the spectrum show where specific elements absorbed light. Bright lines show where elements are emitting light. The stars are burning, and their flames tell us what they're made of, even from thousands of light years away. Every flame you've ever seen is telling you a story. The yellow of a campfire says carbon. The blue of a gas stove says complete combustion. The green sparks in driftwood burning on a beach say salt, sodium and copper from seawater. The colors aren't decoration. They're information. Evidence of what's happening at the atomic level, made visible as beauty. Some colors push the limits of what eyes and cameras can handle. Colors so extreme they break the tools we use to capture them. Vantablack is the blackest black ever created. It absorbs 99.96% of visible light. Almost nothing reflects back. Look at an object coated in Vantablack and your depth perception fails. You can't see contours, shadows, edges. It looks like a flat void cut into reality, a hole in space. Your brain can't process it properly because it expects some reflected light to show shape and dimension. With almost no light coming back, the object disappears into pure darkness. Cameras struggle with it even more. The sensor can't find anything to focus on. No gradients, no detail, just black. Photographs of Vantablack look fake because they are, in a sense. The camera is trying to capture something that's refusing to be captured. The material was developed for space telescopes to reduce stray light and improve visibility of distant stars. But artists wanted it too, because a black, that absolute, creates effects impossible with normal paint. On the opposite end is the pinkest pink, a fluorescent pigment called pink, created by artist Stuart Semple in response to Vantablack being restricted. This pink is so bright, so saturated, that cameras oversaturate trying to capture it. It glows almost unnaturally. Your eyes struggle to look at it for long. The intensity is overwhelming. Too much, beyond what feels normal for reflected light. Then there's the whitest white, a paint developed at Purdue University that reflects 98% of light, even infrared. It's so reflective, it can cool surfaces below ambient temperature just by bouncing away sunlight. Look at it, and your eyes water. Cameras blow out the highlights, turning everything around it grey by comparison. It's white beyond white, past the point where white should be possible. These extreme colours reveal the limits of perception and technology. Human eyes evolved to handle normal ranges, normal blacks that still reflect some light, normal whites that absorb some wavelengths. We're built for a middle ground. Push past those boundaries, and our visual system gets confused. It has no reference, no context. The colors become almost painful to process. Digital cameras have it worse. They're designed to capture detail across a range of brightness. Too dark, and the sensor finds nothing to record. Too bright, and it maxes out, losing all information in a blown-out white. These extreme colors exceed the dynamic range of the sensor, parts of reality that technology can't quite grasp. This is why photographs of deep space often look enhanced. They usually are, not fake, but adjusted. The camera captures a range of brightness that would look muddy and dim to us. So scientists adjust the levels, stretch the contrast, make the faint nebulas and distant galaxies visible. They're translating camera data into something human eyes can appreciate. The colors are real. The brightness is enhanced. Both things are true. Your eyes do this automatically. Your brain adjusts for lighting, for context, for expectation. You see what you need to see, not the raw data of photons. When colors push too far into darkness or brightness, when they become too extreme, both eyes and cameras fail. The color exists, but capturing it, perceiving it fully, requires tools we don't quite have yet. Some colors live at the edge of what's possible to see. Let's leave Earth for a moment, because color looks different everywhere else in the universe. Every planet has its own palette, determined by its atmosphere, its distance from its star, what it's made of. Mars has blue sunsets, the exact opposite of Earth. During the day, the Martian sky glows butterscotch orange because of all the iron oxide dust suspended in the thin atmosphere. Rust particles scatter red and yellow light, but at sunset, when the sun is low and light travels through more atmosphere, blue light scatters forward while red scatters away. The sun itself appears blue, surrounded by a blue glow. Stand on Mars at dusk and you'd see colors reversed from home. Titan, Saturn's largest moon, has an orange sky so thick you can't see the surface from space. The atmosphere is dense with hydrocarbons, organic molecules that absorb blue light and scatter orange and red. Rain falls there, but it's liquid methane, not water. Lakes of methane reflect an orange sky. Everything is tinted amber, a world in monochrome warmth. Gas giants show colors we rarely see together on Earth. Jupiter has bands of white, orange, brown, and red created by different chemicals at different altitudes. Ammonia ice is white. Ammonium hydrosulfide is brown. Complex organic molecules are red. The Great Red Spot is a storm larger than Earth, colored by phosphorus and sulfur compounds churning in the atmosphere. It's been raging for at least 350 years. A permanent hurricane painted in shades we can barely create artificially. Neptune is deep blue, but not from water. Its atmosphere contains methane that absorbs red light and reflects blue. The planet glows sapphire, darker than Earth's sky, richer. Uranus is pale cyan for the same reason, but with less atmospheric activity. These ice giants show you what happens when methane defines the color of a world instead of nitrogen and oxygen. Exoplanets get even stranger. HD 189733b, a planet orbiting a distant star, likely rains glass sideways in 7,000 km/h winds. The glass scatters blue light, making the planet appear deep blue from space. But it's not ocean. It's silicate particles in a hostile atmosphere hot enough to melt lead. A blue planet that would kill you instantly. Some exoplanets orbit double stars. Binary systems where two suns light the sky. The colors mix. A red dwarf and a yellow sun create shadows in two different directions, each shadow tinted by the other star's light. One shadow bluish, the other orange-ish. Stand there and your shadow would be doubled and colored in ways Earth never produces naturally. Then there are planets with no stars. Rogue planets floating through interstellar space, ejected from their solar systems, wandering the galaxy alone. No sunlight, no color except possibly the dim glow of radiation, or the faint light of distant stars. Eternal darkness. Color exists there only as potential, waiting for light that may never come. Every world has its own rules, its own chemistry, determining what colors appear in its sky, on its surface, in its storms. Earth's colors feel universal to us because they're all we've known, but they're specific to this exact mixture of atmosphere, this exact distance from our specific star, this exact composition of elements that happened to gather here. Change any variable and the whole palette shifts. Color is local, planetary, as unique to each world as a fingerprint. Come back to Earth, because even here, sharing the same sunlight and the same landscapes, every species sees a completely different world of color. Dogs see fewer colors than you do. They have only 2 types of color receptors instead of your 3. They're missing the one that detects red. To a dog, red and orange look brownish yellow. Green looks yellow. Purple looks blue. Their world is painted in yellows and blues with shades in between. Not colorblind exactly, just different. They see color, just not your colors. Cats are similar. 2 color receptors, limited color range, but they see better in dim light because they have more rod cells, the receptors that detect brightness instead of color. They traded color for night vision. In twilight, when your world fades to gray, cats still see clearly. Different priorities, different perceptions. Birds see better than you do. Most birds have 4 color receptors. 4, they see colors you literally cannot imagine. Because your brain has no way to process them. Birds see ultraviolet as a distinct color, separate from violet. Flowers that look plain yellow to you have ultraviolet patterns visible to birds, guiding them to nectar. Some birds have plumage that looks drab to humans, but brilliant to other birds. Entire visual signals happening in wavelengths you're blind to. Then there's the mantis shrimp. 16 color receptors. 16. You'd think they see a rainbow beyond human comprehension. And they do see ultraviolet and polarized light. But here's the twist. Scientists believe mantis shrimp actually see color worse than you do. They don't process color the way you do. Instead of comparing signals between receptors like your brain does, each receptor seems to fire independently. They see more wavelengths, but with less subtlety. It's like having 16 separate channels instead of a blended spectrum. Different isn't always better, just different. Bees see 3 colors like you do, but shifted. They see ultraviolet, blue, and green. Red is invisible to them, dark. A rose looks black to a bee. But white flowers often reflect ultraviolet, making them glow with color you can't see. Bees navigate a world where some flowers shine and others disappear, guided by patterns of light that exist just outside your visual range. Snakes with heat pits see infrared as color. Their brain integrates thermal vision with regular vision, creating a combined image where warm things glow against cooler backgrounds. A mouse at night is a bright spot of color to a viper. Living things announce themselves in heat signatures painted across the snake's perception. Some fish see polarized light. Light waves vibrate in specific directions, and these fish can detect which direction. It helps them navigate, detect prey, see through water glare. You can't see polarization except through special filters. To these fish, it's natural, constant, part of their basic color experience. Every animal inhabits its own sensory universe. Same physical light, same wavelengths bouncing around, but completely different experiences. A bird, a dog, a bee, and a human standing in the same garden see 4 different gardens. Each one is real. None is more correct than the others. They're all just different ways of translating electromagnetic radiation into conscious experience. Different tools, different perceptions, different realities constructed from the same fundamental physics. But you don't even see the same colors as other humans. Not exactly. Every person's color perception is slightly different, shaped by genetics, experience, and the unique wiring of their individual brain. Remember the dress, the photograph that broke the internet in 2015. Some people saw it as blue and black, others saw white and gold. Same image, same pixels, completely different colors. It wasn't a trick or an optical illusion. Both groups were genuinely seeing different colors because their brains were making different assumptions about the lighting. Your brain constantly guesses at what color things really are by factoring in the light source. Is this scene lit by warm sunlight or cool shadow? Indoor lighting or daylight? Your brain adjusts automatically, so a white shirt looks white in both sunlight and lamplight, even though the actual wavelengths reaching your eyes are completely different. This is called color constancy. The dress photo was ambiguous. It could be interpreted as a blue dress in bright light or a white dress in shadow. Your brain picked one interpretation based on your personal experience with lighting. People who spend more time outdoors tended to see white and gold, assuming the dress was in shadow. People who spend more time indoors tended to see blue and black, assuming the dress was in artificial light. Your history shaped your perception, but it goes deeper. The lenses in your eyes yellow as you age. By the time you're 60, you're seeing the world through a slightly amber filter. Blues look less vibrant. Whites look warmer. You don't notice because the change is gradual, but you're literally seeing different colors than you did as a child. An elderly person and a young person looking at the same white wall see different shades. Some people are tetrachromats. They have 4 types of color receptors instead of 3. Mostly women, because the gene for the 4th receptor is on the X chromosome. These people see more colors than you do. They distinguish shades that look identical to you. Where you see one beige, they see 6 different beiges. They exist in a richer color space, though they may not realize it because they have no way to compare their experience to yours. Then there's the language effect we mentioned earlier. Russian speakers have separate words for light blue and dark blue, and brain scans show they process these as truly different colors, not shades of one color. The language literally rewired their perception. Similarly, some cultures with many words for different greens see distinctions invisible to English speakers. Even the lighting you grew up with matters. If you spent childhood in warm-lit rooms, you calibrate colors differently than someone raised in cool daylight. Your brain builds its color categories from experience, and those categories stick with you, subtly shifting what you see. Color perception is personal. You'll never know if your experience of red matches mine exactly. We both call it red. We agree it's red. But the internal experience, the quale of redness, might be different. We have no way to compare, no way to step into another person's consciousness and see through their eyes. This isn't a problem to solve. It's just reality. Color is both shared and private, both objective and subjective, both physics and consciousness. And every person carries their own unique version, built from their genes, their history, their language, their brain's particular way of turning wavelengths into experience. So what comes next? Color isn't finished evolving. Technology is pushing the boundaries of what colors we can create, display, and even see. Quantum dots are changing screens right now. These are tiny crystals, each one just a few nanometers across, that emit pure colors when electricity passes through them. The size of the crystal determines the color. Bigger dots emit red, smaller dots emit blue, medium dots emit green. And because they're so precise, they create colors more saturated than any previous screen technology. The reds are redder. The blues are bluer. The range of colors your TV can display is expanding. Some quantum dot displays can show colors that exist in nature, but were impossible to reproduce on screens before. Deep ocean blues, sunset oranges, colors that used to get compressed and dulled by older display technology can now appear in their full intensity. You're seeing more of reality through your screen than you could a decade ago. Metamaterials take it further. These are artificial structures engineered at scales smaller than wavelengths of light. They can create color through structure alone, like butterfly wings, but more precise. Researchers have created materials that change color when you tilt them, or when temperature shifts, or when voltage is applied. Color that responds. Color you can control. These materials could lead to displays that need no power to maintain an image, or paint that changes shade on command. Then there's genetic engineering. Scientists have successfully given mice human color vision by adding a third color receptor gene. The mice went from seeing 2 primary colors to seeing 3. They gained color vision they never had before. The same technique could theoretically work in humans. Someone born colorblind could potentially gain normal color vision through gene therapy. Or someone with normal vision could gain a 4th receptor, becoming a tetrachromat artificially. Imagine seeing colors you've never seen before. Not new shades of existing colors, but genuinely new colors in categories that don't exist for you now. It would be like the Himba person suddenly able to distinguish blue, or a dog suddenly seeing red. Your visual world would expand into ranges that were invisible before. But here's the question: would more colors make life better? Or would it be overwhelming? Your 3-color system is elegant, efficient. It gives you enough information to navigate the world without drowning you in excessive detail. 4 types of receptors means 4 times as much color information to process. Your brain would need to adapt. The experience might be beautiful. It might be exhausting. We don't know. Some philosophers argue that our limited color perception creates meaning through constraint, that having fewer colors makes each one more significant. A world of infinite colors might be a world where no color stands out, where everything blends into an overwhelming spectrum, like having too many words for one concept. Eventually, the distinctions stop mattering. Others argue that more perception is always better, that seeing more of reality brings us closer to truth, that limitations are just problems waiting for solutions. Both might be right. Technology will likely give us the option eventually. Better screens, genetic modifications, neural implants that add new sensory channels. The colors of the future might include wavelengths we're blind to now, and we'll have to decide if we want them. If expanding our perception of color is worth the cost of losing the simplicity we have now. Let's come back to where we started. To color. Simple color. The thing you've been seeing your whole life without thinking about it. You know now that color doesn't exist in objects, that it's created by your brain from wavelengths of light, that magenta is invented, that the sky's blue is an illusion, that ancient people might have seen the world differently because they lacked words for certain colors. That blue is rare in nature, that pink used to be masculine, that you're missing most of the electromagnetic spectrum, that red changes your heart rate, that impossible colors hide in the gaps, that traffic lights use physics and culture together, that some colors have gone extinct, that rainbows are personal, that things can glow from chemistry, that black and white might not be colors at all, that flames tell chemical stories, that extreme colors break cameras, that alien worlds paint themselves in foreign palettes, that every animal sees differently, that you see differently from every other human, that the future might bring colors you can't imagine yet. And after all of that, after pulling color apart into physics and biology and culture and perception, what's left? Beauty. That's what's left. The simple fact that wavelengths of electromagnetic radiation, filtered through atmosphere and reflected off surfaces and detected by proteins in your eyes and interpreted by neurons in your brain, create something you experience as beautiful. That's not less amazing for being explained. It's more. You're a biological machine that turns physics into poetry. That's what seeing color is. Raw data from the universe, transformed by your body and mind into conscious experience. Every sunset you've ever watched was you doing that, converting photons into feeling, making something subjective from something objective, creating meaning from meaningless wavelengths. And here's what matters. The sunset you see is yours. Nobody else sees that exact sunset. Your eyes, your brain, your history, your position in space. It's personal, but it's also universal. Everyone who's ever lived has looked up at colored skies and felt something. The experience is both individual and shared, private and collective, unique and common. Color connects you to everything, to the physics that governs stars and fire, to the biology you share with bees and birds, to the culture that taught you what colors mean, to the language that gave you categories to see them by, to other humans who see differently but call it the same names, to the universe itself, sending light through space for billions of years until it reaches your eyes and becomes experience. That's worth paying attention to, worth noticing, worth letting fill you with calm wonder as you settle into sleep. Because you're not just seeing colors, you're participating in them, creating them, making them real through the act of perception. Look around you now, at whatever colors are near you in this moment. They're not what you thought they were. They're stranger, more constructed, more personal, more beautiful, and they're yours, your private translation of light into experience, your unique window on reality. If you enjoyed this journey through the science of color, please like this video and subscribe. Tomorrow, we'll explore something equally amazing, and let me know in the comments where you're watching from. I'd love to know where in the world you are, seeing your own unique colors. Now, close your eyes, let the colors fade and rest well.